In the autumn of 1944, at an isolated air base in the Philippines, something extraordinary was about to happen. An American P-51 Mustang fighter, gleaming in its silver paint, had been forced to make an emergency landing in territory controlled by Japanese forces. The pilot managed to escape, but the aircraft remained there, almost intact, like an unexpected gift for the engineers of the Empire of Japan. What they didn't know was that this machine contained within it not just an engine, but a revelation that would completely change their understanding of the war they were waging. This is the story of how a group of brilliant, dedicated, and patriotic engineers, by meticulously disassembling that Packard Merlin engine, piece by piece, bolt by bolt, arrived at a devastating conclusion. A conclusion that went far beyond simple technical specifications or performance figures. They discovered something that no military communique, no battle bulletin, and no war propaganda could ever reveal with such clarity. The true extent of the industrial gap between Japan and the United States of America. Before we continue with this extraordinary story, if you appreciate detailed and well-researched historical content, don't forget to subscribe to the channel and leave a comment telling us what time you're watching this documentary. Now, let's go back to that hangar in the Philippines, where scientists were about to confront a truth impossible to ignore. The story of the P-51 Mustang begins not with a tale of triumph, but with a desperate need. In the early 1940s, the British Royal Air Force was facing a critical problem. Its fighters, though brave and well-piloted, simply couldn't escort bombers on long-range missions over occupied Europe. The distance was too great, the fuel too scarce, and the losses unacceptable. The British needed something new, something revolutionary, and they needed it quickly. North American Aviation, a relatively young company in California, received a challenge that seemed impossible. They had only 120 days to design a completely new fighter jet. 120 days to create something that could change the course of aerial warfare. Most experts considered the deadline absurd, impractical, a fantasy born of desperation. But Chief Engineer Edgar Schmid, a German-born American with a brilliant mind and unwavering determination, accepted the challenge. Schmid and his team worked with an intensity bordering on obsession. They slept at their drawing tables, ate in front of their calculations, lived and breathed every curve, every angle, every millimeter of that project. And something magical happened. In just 117 days, 3 days before the impossible deadline, the prototype was ready. It was an elegant aircraft, almost sensual in its lines, with a fuselage that seemed to have been sculpted by the wind. But there was a problem. The Mustang's original engine, a first-generation Allison, was adequate but not exceptional. The aircraft flew well at low altitudes, but lost significant performance when climbing to combat altitudes. It was like having a 100-meter sprinter trying to compete in a marathon. Good but not good enough. And in war, good enough meant failed missions and increased risks for the crews. That's when someone had a brilliant idea. What if they replaced the Allison engine with the Rolls-Royce Merlin, the same engine that powered the legendary British Spitfires? The Merlin was a masterpiece of British engineering, a supercharged engine that maintained its power even at the highest altitudes, where the thin air turned other engines into dead weight. But there was a problem. The British needed every Merlin they could produce for their own aircraft. The solution came from America. The Packard Motor Car Company, famous for its luxury automobiles, received the Merlin plans and the mission to mass-produce it in American territory. But Packard's engineers didn't just copy the British design. They studied it, understood its essence, and then applied American mass production methods, transforming what was a handcrafted engine into a precision-manufactured product on an industrial scale. The result was the Packard V1650 Merlin, and when that engine was installed in the P-51, something magical happened. The aircraft was transformed. From a competent low-altitude fighter, it became the best long-range fighter of the entire Second World War. With additional fuel tanks, the P-51 Mustang could escort bombers from London to Berlin and back. Could fight at any altitude. It could outmaneuver and outrun any enemy fighter in the European skies. German pilots, who had previously held an advantage over Allied bombers, suddenly found themselves facing significant challenges against the silver Mustangs that appeared to protect the formations. Luftwaffe General Adolf Galland, one of the greatest German aces of the war, later said that when he saw the P-51s flying over Berlin, he knew that air supremacy had changed hands. Allied air power, mounted on the wings of the Mustang, had become dominant. But while this was happening in the European skies, on the other side of the world, the Empire of Japan was waging its own desperate war. And it was in this context that the P-51 made its forced landing in the Philippines. For the Japanese engineers, it was an unprecedented opportunity. They had seen these aircraft in combat, had witnessed their terrifying performance, had lost confrontations against them. Now, finally, they would have the chance to understand the secret behind that formidable machine. The captured aircraft was carefully transported to a secret facility in Japan. The news spread rapidly among the aeronautical engineering community. The best specialists were summoned. Men who had dedicated their lives to the study of aviation, who had designed Japanese fighter planes themselves, who knew every nuance of available aeronautical technology. They arrived with notebooks, measuring instruments, and an almost religious determination to unravel the mysteries of that American machine. What followed was a meticulous study that lasted weeks. Every panel was removed and photographed. Every system was mapped and documented. Every joint, every rivet, every wire was examined with the precision of surgeons performing an autopsy. But the heart of the investigation, the main focus of all that attention, was the engine. That 1,500 horsepower Packard Merlin that made the Mustang fly like no other aircraft in the Japanese arsenal could. The engineers began with the exterior. They measured every dimension, recorded every connection, and mapped every auxiliary system. Then, with special tools that had to be manufactured specifically for that task, they began to disassemble the engine. Layer by layer, component by component, the Merlin revealed its secrets. And with each piece they removed, with each system they unveiled, something extraordinary began to happen in the minds of those engineers. The first shock came when they examined the materials. The engine block was made of an exceptionally high-quality aluminum alloy, uniform throughout, without variations or detectable impurities. The pistons were forged with near-perfect precision. The connecting rods, which linked the pistons to the crankshaft, were works of engineering art, lightweight yet incredibly strong, manufactured with special steels that Japan simply did not have the capacity to produce on a large scale. But it wasn't just the materials that impressed. It was the way everything fit together. The tolerances between the moving parts were measured in hundredths of a millimeter. The crankshaft, a massive piece that converted the reciprocating motion of the pistons into rotation, was balanced with a precision that Japanese engineers had never seen before. There were no unnecessary vibrations, no premature wear, no wasted energy. Each component was optimized not only to function, but to function perfectly for hundreds of hours of extreme operation. The two-stage supercharging system proved to be a marvel of complex engineering. Two compressors working in series compressed the rarefied air of high altitudes and fed it to the cylinders with enough pressure to maintain power even at 10,000 meters. The intercooler system, which cooled the compressed air before it entered the cylinders, used a radiator designed with flow channels optimized by advanced mathematical calculations. Every detail revealed layers of knowledge, experience, and technical skill. One of the senior engineers, a man named Horikoshi, who had designed the famous Zero fighter, was particularly fascinated by the air-fuel mixture control system. It was a surprisingly elegant mechanism that automatically adjusted the fuel-to-air ratio depending on altitude, temperature, and the power demanded by the pilot. It didn't require constant pilot intervention. It was intelligent, responsive, and reliable. The Zero, in comparison, required the pilot to manually adjust the mixture during flight, a task that demanded constant attention and considerable experience. But perhaps the most revealing aspect wasn't any specific component, but something more subtle, deeper, more disturbing. It was the quality of the manufacturing. Every screw was identical to the next. Every washer, every nut, every electrical connector followed absolutely uniform patterns. There was no variation. There were no handmade parts to compensate for imperfections. There were no individual adjustments needed during assembly. Everything was interchangeable, everything was standardized, everything was the product of a mass production system operating at a level of sophistication that Japan was years, perhaps decades, away from achieving. The engineers took samples of the materials and sent them for metallurgical analysis. The results were devastating. The special steels used in the engine contained alloying elements that Japan simply did not have in sufficient quantities. Nickel, molybdenum, chromium in specific concentrations that produced superior mechanical properties. Worse still, even if Japan had access to these materials, it did not possess the high-precision heat treatment furnaces necessary to properly process these alloys. The aluminum alloy used in the engine block proved to be an even greater problem. Analyses showed it was a special alloy developed specifically for aeronautical applications, with extraordinary strength even at high temperatures. Producing this alloy required precise temperature control during casting, something the Japanese facilities could not consistently replicate. When they tried, the rate of defective parts was unacceptably high, making production economically unviable. A younger engineer, Tanaka, was tasked with calculating how long it would take Japan to develop the necessary capabilities to produce an equivalent engine. He worked for days, consulting experts in various fields, examining Japanese industrial capabilities, and making projections based on available resources. His conclusion was presented in a report that circulated among the highest levels of the Japanese military command. He estimated that, under current conditions, Japan would need at least 5 to 7 years just to develop the necessary metallurgical infrastructure. Another 3 to 5 years would be needed to perfect the manufacturing processes. And this assumed that all the necessary resources would be available, that there would be no interruptions due to the war, and that the necessary technical knowledge could be developed or acquired. But there was an even more fundamental problem that gradually became clear to the Japanese engineers. It wasn't just about an engine. It wasn't just about metallurgy or manufacturing precision. It was about systems. The Packard Merlin was the product of an entire industrial ecosystem. The tools that manufactured the parts were products of other specialized factories. The precision measuring instruments came from manufacturers dedicated exclusively to metrology. The special materials were produced in steel mills equipped with cutting-edge technology. The engineers who designed the engine had been trained at universities with decades of experience in aeronautical research. The workers who assembled the engines worked with detailed procedure manuals, were systematically trained, and operated on assembly lines designed by experts in industrial efficiency. In other words, the engine was not just a product. It was the visible tip of an immense iceberg of industrial capacity, technical knowledge, systematic organization, and material resources. And this iceberg was simply incomparable in scale to what Japan possessed. The United States was not only better at making airplane engines. They had built an industrial machine of a magnitude that the Japanese, looking at those parts scattered across the workbenches, were finally beginning to truly understand. One of the darkest moments of this investigation came when engineers calculated the production rate. They discovered through captured documentation that Packard produced approximately 2,000 Merlin engines per month at its facilities. 2,000 engines per month. The factory operated in 3 shifts, 24 hours a day, 7 days a week. It employed tens of thousands of skilled workers. It had supply lines that brought materials from all over the American continent. And Packard was just one of several American manufacturers of high-performance aircraft engines. Japan, at its peak production during the war, was able to manufacture perhaps 400 to 500 high-performance aircraft engines per month, of all types combined. And these engines, while competent at the beginning of the war, now proved to be inferior in performance, less reliable, and more difficult to maintain. The difference was not marginal. It was abysmal. It was the difference between 2 industrial civilizations operating on completely different scales. Horikoshi, the designer of the Zero, wrote in his private diary about the experience of examining the Merlin engine. His words, discovered years after the war, reveal the depth of the psychological impact of that revelation. He wrote that he had dedicated his entire life to creating aircraft that could defend his country. He had taken pride in the Zero, in its agility, its range, its elegance. But as he held a Merlin connecting rod in his hands, as he examined its metallurgical perfection, as he understood the complex systems that allowed that engine to function so efficiently, he felt something he had never experienced before. It wasn't despair, it wasn't defeat, but a cold and terrible clarity. He realized that Japan was fighting an industrial war against an adversary operating in a completely different dimension. This perception was not confined to the group of engineers. Reports began circulating among military commanders, government ministers, and those who made decisions about the future of the war. The reports were technical, full of specifications and detailed analyses, but their message was impossible to ignore. Japan was losing not only battles, but the industrial competition that sustained the war effort. And this industrial competition had already been decided long before the conflict began. It is important to understand the broader context of this revelation. Japan had entered the war with the belief, widely held by its military and political leadership, that warrior spirit and dedication could compensate for material inferiority. The tradition of Bushido, the way of the warrior, emphasized courage, sacrifice, and determination over material considerations. Japanese pilots were rigorously trained, extremely dedicated, and willing to make great sacrifices for the mission. This determination had brought impressive victories early in the war. But the Merlin engine told a different story. It demonstrated that, in modern warfare, spirit was not enough. Determination could not replace two-stage superchargers. Courage did not compensate for superior steel alloys. The conflict had evolved beyond a contest of wills to become a competition of industrial systems. And in that competition, material advantage was decisive. An extremely skilled Japanese pilot in an inferior fighter would still face a significant disadvantage against an average American pilot in a P-51 Mustang. The equation was clear in its simplicity. The engineers also examined other aspects of the P-51 that revealed fundamental differences in design philosophy. The Mustang had a high-quality radio system, allowing clear communication between pilots even during intense combat. Japanese fighters had lower-quality radios, often removed by the pilots to save weight. The Mustang had armor protecting the pilot and self-sealing fuel tanks that could withstand damage without catching fire. The Zero had been designed without armor, maximizing agility at the expense of protection. These design choices revealed profoundly different philosophies. The Americans designed aircraft assuming that pilots were valuable assets that needed to be protected, that they could be trained and replaced, but that their experience should be preserved whenever possible. The Japanese had designed to maximize combat performance, prioritizing the mission over pilot protection. Early in the war, when veteran Japanese pilots flew the Zeros, this philosophy worked. But as these experienced pilots were lost and replaced by less trained novices, the absence of protective features became a significant disadvantage. The Mustang's flight control system also revealed subtle but important differences. The controls were harmonized, meaning that the force required to move the stick was balanced in all directions, facilitating precise maneuvers. The hydraulic system was redundant, with multiple paths for hydraulic fluid, so that damage in one location did not compromise the entire system. Small details, but multiplied by thousands of design decisions, created an aircraft that was not only powerful, but also practical, reliable, and forgiving of pilot error. One particularly impressive aspect was the technical documentation. The captured P-51 came with maintenance manuals that the Japanese engineers examined with fascination. These manuals were masterpieces of technical clarity. Each system was explained with detailed diagrams, step-by-step instructions, precise specifications for maintenance tolerances, and checklists for different types of repairs. A relatively inexperienced mechanic, following these manuals, could keep the engine running properly. Japanese maintenance manuals, in comparison, were often vague, assumed a high level of knowledge on the part of the mechanic, and required improvisation and experience. The American philosophy was to make maintenance a systematic process that anyone properly trained could perform. The Japanese approach relied more on experienced craftsmen with in-depth knowledge. In a prolonged war where experienced mechanics were lost and needed to be quickly replaced, the difference was significant. As the study of the P-51 continued, Japanese engineers began requesting information about other aspects of American industrial production. What they discovered was even more impressive. The United States wasn't just producing superior fighter planes. They were producing everything in unimaginable quantities. Bombers by the thousands, warships in weeks instead of years. Tanks, trucks, small arms, ammunition, fuel, food, clothing, medical equipment. It was a torrent of material flowing across the Pacific Ocean in quantities that defied comprehension. One of the engineers gained access to military intelligence on American industrial production. The numbers were hard to believe. In 1944, the United States produced over 96,000 aircraft. 96,000. Japan, in that same year, produced approximately 28,000 aircraft of all types. And many of the Japanese aircraft were obsolete in design, inferior in performance, less reliable in operation. The quantitative difference was bad enough. The qualitative difference made the situation desperate. Naval production told a similar story. The United States had developed shipbuilding techniques that allowed them to weld complete ships together in a matter of weeks. Escort carriers, cargo ships, battleships, destroyers, all rolled out of shipyards at a rate the Japanese couldn't match, even if they focused exclusively on shipbuilding. And the Americans were doing this while simultaneously supplying material to allies in Europe, maintaining their own armed forces, and continuing to produce civilian goods for their population. It was this dimension that the Merlin engine revealed in its most concentrated form. It wasn't an engine. It was a symbol of a completely different kind of industrial society. A society that had mastered mass production, that had organized science and engineering on a national scale, that had created training systems producing millions of skilled workers, that had developed supply chains spanning entire continents, that had integrated universities, research laboratories, factories, and armed forces into a single coordinated mechanism of war production. Japan had industrialized rapidly during the Meiji Restoration, transforming itself from a feudal society into an industrial powerhouse in just a few decades. It was an impressive achievement. But the type of industrialization Japan had achieved was fundamentally different from that which existed in the United States. Japanese industry was concentrated, controlled by large family conglomerates, dependent on imports of natural resources, and limited by a lack of territory and population compared to the adversaries it now faced. America, in contrast, was a continent rich in natural resources of almost every kind necessary for modern industrial production. It had abundant oil, coal, iron or copper, aluminum, and rare earth elements. It had a huge, educated, and increasingly specialized population. It had a university system that produced engineers, scientists, and technicians in numbers that Japan could not match. It had a culture of business innovation that encouraged experimentation, accepted failure as part of learning, and rewarded success generously. Horikoshi and the other senior engineers began discussing amongst themselves, in private conversations that were not officially recorded, the implications of what they had discovered. Some argued that honest reports should be sent to the highest ranks, informing leadership of the true situation. Others feared that such reports would be considered defeatist, that they could be punished for demoralization, that the truth was politically impossible to communicate in a system where pessimism was equated with treason. Eventually, reports were sent, but they were carefully worded, full of technical language that obscured the central message. They talked about differences in metallurgy, about production systems, about performance specifications. But the real message, the devastating truth that those engineers had discovered, was difficult to articulate in official reports. How do you explain to generals that the war is lost not for lack of courage or strategy, but because the enemy operates on an industrial scale that makes victory mathematically impossible? Some of the military commanders who read the reports understood the implications. But the war machine had its own inertia. Plans had already been made, strategies established. Propaganda had promised victory to the Japanese people. To admit that the war was impossible to win would be to admit that so many sacrifices had been made in a lost cause. It was psychologically impossible for many in leadership to confront this truth. So the war continued, even when those in the know understood how it would end. As 1944 turned into 1945, the situation in the Pacific deteriorated rapidly. Island after island was captured by American forces. The once dominant Japanese Navy was reduced to a fraction of its former power. The Japanese Air Force was suffering severe losses, not in decisive battles, but through continuous attrition. The ratio of losses dramatically favored the Americans. and the United States could replace its losses in days. Japan took weeks or months if it could manage at all. Kamikaze attacks, those extreme tactics where pilots directed their aircraft against enemy ships, were often presented as demonstrations of Japanese warrior spirit. But the engineers who had studied the Merlin understood another dimension of this strategy. It was also a reflection of the fact that Japanese pilots in inferior aircraft faced immense challenges in conventional combat against superior American fighters. It represented a desperate tactical adaptation to the reality of technological disparity. In August of 1945, 2 nuclear attacks occurred on Hiroshima and Nagasaki. To the world, these events represented the pinnacle of the technological and scientific capabilities of the time, developments that accelerated the end of the conflict. But for the engineers who had studied the Merlin engine months before, these developments confirmed on a dramatic scale what they had already understood. They had already seen, concentrated in that 27-liter engine, evidence of American industrial and scientific capacity. The events of August merely made visible to the whole world what they had discovered months earlier through technical analysis. After the war, many of these engineers participated in the reconstruction of Japan. Some went to universities where they taught a new generation of engineers. Others worked in nascent industries, applying lessons learned during studies of foreign technology. Horikoshi eventually worked on civilian aircraft projects, contributing to the development of the post-war Japanese aeronautical industry. But all carried memories of those days studying the P-51, that moment of revelation when they truly understood the magnitude of the challenge their country had faced. There is a rare photograph, kept in the archives of an aeronautical museum in Tokyo, that shows some of these engineers gathered around the disassembled Merlin engine. It is a powerful image. Middle-aged men, wearing white lab coats, surrounded by metal parts neatly arranged on tables. Their faces are serious, focused, but there is something more in their expression. A kind of respect, perhaps, or recognition. They are looking not just at an engine, but at a mirror reflecting capabilities that their own country did not possess. Years after the war, in interviews and memoirs, some of these engineers spoke about that experience. Their words are remarkably consistent. They do not speak bitterly about the Merlin engine. There is no resentment about American technical superiority. Instead, there is a kind of professional admiration, an engineer-to-engineer recognition of the excellence of what they had examined. They described the engine as perfect, as a masterpiece, as the standard we aspired to achieve. But they also talk about the broader lesson. Tanaka, the young engineer who calculated the time it would take for Japan to achieve equivalent capabilities, said in an interview in the 70s that the experience of studying Merlin completely changed his understanding of what it means to be a modern industrial nation. He realized that technology does not exist in isolation. It emerges from educational systems, scientific culture, industrial organization, access to resources, philosophies about human value and efficiency. You can't simply copy a product and expect to replicate success. You need to build the entire ecosystem that makes that product possible. This lesson would be remarkably applied in post-war Japan. The country did not simply try to copy Western products. Instead, it focused on building fundamental capabilities. It invested massively in education, especially in science and engineering. It developed a culture of continuous improvement, capturing the philosophy of quality and efficiency observed in American products but adapting it to the Japanese context. It created partnerships between universities and industry, facilitating the transfer of knowledge between research and practical application. The result, decades later, was the emergence of Japan as a global industrial powerhouse in electronics, automobiles, robotics, and other high-tech fields. The country that had been devastated by war, that had confronted its industrial limitations so directly by examining that Merlin engine, transformed itself into one of the world leaders in precision manufacturing and technological innovation. It is one of the most remarkable stories of recovery and transformation of the 20th century. But let's return to that hangar in the Philippines, to that moment of discovery. There is something profoundly human in this story that transcends technical specifications and industrial analyses. These Japanese engineers were patriots who loved their country. They had dedicated their lives and skills to defending Japan. They believed in the righteousness of their cause. And then, upon examining that engine, they were forced to confront a truth that contradicted everything they had been taught to believe about war. It wasn't a quick revelation, a single moment of clarity. It was gradual, cumulative, building up piece by piece, specification by specification, until the weight of the evidence became impossible to ignore. And when they finally fully understood, they had to bear that knowledge knowing they could do little to change the course of the war. They had to keep working, keep trying, keep supporting the war effort even knowing it was doomed. It's hard to imagine the psychological toll of that situation. There are interesting parallels between this story and other moments in human history where individuals confronted difficult truths about their societies. German scientists at the end of World War II realizing that the Third Reich was doomed. Soviet engineers during the Cold War recognizing technological lags compared to the West. In each case, technically competent professionals are forced to reconcile patriotic loyalty with objective reality. It is a dilemma without easy answers. What makes the story of the Merlin engine particularly powerful is its specificity. It wasn't abstract reports on industrial capacity or production statistics. It was a physical, tangible object that they could touch, measure, and fully understand. There was no room for denial, for propaganda, for self-deception. The engine was there, disassembled on the tables, each piece silently bearing witness to an undeniable truth. Sometimes, inanimate objects can teach lessons that no amount of words could convey. It's also worth considering the perspective of the American engineers who designed and produced that engine. For them, the Merlin was just another product in a product line. Important, yes. Well-made, certainly. But not unique. It was part of a system where excellent engines were the standard expectation, not the exception. They didn't design the Merlin thinking it would be a symbol revealing to adversaries the extent of their industrial superiority. They simply did their job, applied available knowledge, followed established practices, and used the resources they had at their disposal. And the result was something that would completely transform the understanding of engineers on the other side of the world about the war they were fighting. There's an irony in this story. The P-51 Mustang was initially designed for the British Air Force, not the American one. The Merlin engine was originally British. So, in a sense, that engine which revealed so much to Japanese engineers about American industrial capability was, in its conception, a product of British engineering adapted and mass-produced by American industry. It was a transatlantic collaboration, an example of how allies can combine their forces to create something greater than either could achieve alone. This capacity for international collaboration, for integrating knowledge and capabilities from different nations, was in itself an advantage that the Axis powers, with their ideologies of national supremacy, never managed to adequately replicate. The story of the Merlin engine and Japanese engineers also reminds us that wars are won not only on battlefields, but in factories, laboratories, universities, and design studios. The courage of soldiers and the skill of generals are important, but in modern warfare, industrial capacity is often decisive. The Soviet Union survived the Nazi invasion not only because of the bravery of the Red Army, but because it managed to evacuate and reestablish its industrial base in the Urals, beyond the reach of German bombers. Nazi Germany lost despite excellent engineers and dedicated soldiers because it could not match the combined industrial output of its adversaries. Japan learned this lesson the hard way, and it's worth noting that the country never forgot. Modern Japan's emphasis on education, research and development, and quality manufacturing can be directly traced to the lessons learned during the war. The Merlin engine indirectly influenced the development of an entire nation in the following decades. It's a consequence that the engineers at Packard and Rolls-Royce who designed that engine could never have foreseen. Today, decades after those events, the P-51 Mustang is revered as one of the greatest fighter planes in aviation history. Aviation enthusiasts restore original examples, fly them in air shows, and preserve every detail of their history. The characteristic sound of the Merlin engine, that deep roar that once filled Luftwaffe pilots with fear, now evokes nostalgia and admiration. Museums around the world display carefully preserved Mustangs, explaining their historical importance to new generations. But the story of the Japanese engineers studying that captured engine is rarely told. It's a footnote in the larger history of World War II, an obscure episode known mainly to aviation history specialists. However, it's a story that deserves to be remembered because it reveals something profound about human nature, about confronting difficult truths, about the role of technology in history, about how individuals respond when their understanding of the world is fundamentally challenged. These engineers were ordinary men doing extraordinary work under impossible circumstances. They were not heroes in the traditional sense. They did not fight battles, they did not save lives, they did not perform feats of physical courage. But they demonstrated a different kind of courage. The courage to see clearly, to recognize objective truth even when it contradicts deeply held beliefs, to carry difficult knowledge with dignity. This form of intellectual courage is as valuable as physical courage, though it is rarely celebrated in the same way. We can speculate about the conversations that took place in that hangar during long nights as they worked. They probably discussed technical specifications, debated interpretations of complex diagrams, shared discoveries about particular systems. But we can also imagine quieter moments, when the magnitude of what they were discovering weighed on them, when they looked at those perfect pieces spread out on the tables and contemplated what it meant for their country, for the war, for the future. These moments of silent reflection, not recorded in any official report, were perhaps the most important of all. Technology has this peculiar quality of revealing truths that transcend its immediate purposes. A modern smartphone, for example, is more powerful than the computers that guided the Apollo missions to the moon. This fact says something profound about technological progress, about miniaturization, about the democratization of computing. Similarly, that Merlin engine, seen only as an engine, was impressive. But seen as a symbol, as the physical crystallization of industrial capabilities, it revealed truths about the world that statistical data and reports could never convey with equal impact. In retrospect, knowing how history unfolded, it's easy to see the Japanese engineers' discovery as inevitable. Allied material superiority was evident in battle results, production statistics, and the relentless march of American forces across the Pacific. But for those living through the events without the benefit of hindsight, the situation was less clear. Propaganda promised future victories, strategies were continually adjusted, hopes persisted that a change of fortune might occur. The Merlin engine cut through this fog of uncertainty and self-delusion with brutal clarity of undeniable physical evidence. There is also an almost tragic aspect to this story. These engineers represented the best of Japanese technical education. They were brilliant, dedicated, patriotic men. Had they lived under different circumstances, they could have contributed to the peaceful development of their country, created technologies that benefited humanity, and taught future generations of engineers. Instead, their skills were directed toward the war effort, and their moment of greatest technical clarity came through understanding the reality of industrial disparity. It is a redirection of human talent that reflects the difficult circumstances of the time. World War II was, in many respects, a competition of engineers. Radar, primitive code-breaking computers, jet propulsion, and eventually nuclear power, all these technologies emerged or were accelerated by the conflict. Engineers on all sides worked intensely to create technological advantages that could change the course of events. The Merlin engine was just a small part of this massive technological competition, but its story encapsulates many of the larger dynamics at play. The importance of industrial infrastructure, the role of education and scientific research, the interplay between innovation and mass production, and how technical advantages translate into decisive outcomes. But history also reminds us of the limitations of technology. Japan had excellent engineers. It had a tradition of meticulous craftsmanship. It had dedication and discipline. What it lacked was not individual talent, but systems that could scale that talent across an entire society, infrastructure that could transform brilliant designs into mass-produced products, and the material resources necessary to sustain industrial production on the scale needed for modern warfare. Technology by itself is not enough. It needs to be embedded in social, economic, and political systems that can support and sustain innovation over time. The generations that came after these events live in a profoundly different world. World War II ended more than 80 years ago. Japan and the United States transformed from historical adversaries into close allies. Japanese industry, far from remaining inferior, became a world leader in many areas. The Merlin engine, that devastating revelation of American industrial superiority, is now a relic, an object of historical interest but no longer cutting-edge technology. The world has changed in ways that those engineers in 1944 could not have imagined. However, the lessons from that experience remain relevant. In any competitive field, be it business, sports, academia, or politics, there is value in honestly understanding one's own capabilities relative to competitors. Self-deception may be comforting in the short term, but it is destructive in the long term. The courage to see clearly, to recognize where one is deficient, to learn from adversaries, is fundamental to improvement. The Japanese engineers demonstrated this courage. It would be painful to admit, but their discoveries eventually contributed to Japan's post-war transformation. There is also a lesson about the nature of war itself. The Merlin engine revealed that the outcome of the war was essentially already determined before decisive battles occurred. Japan's industrial inferiority meant that sustained victory was impossible against a coalition including the United States, regardless of courage, strategy, or tactical skill. This insight is important. It suggests that some wars perhaps should never be fought, that prudence and diplomacy are worth more than military adventurism when real chances of success are carefully assessed. It's impossible not to think about the individuals involved in this story. The Japanese engineers, carrying knowledge of industrial realities while continuing to work. Japanese pilots flying missions in aircraft they knew were inferior. Factory workers in Japan producing equipment that technicians knew was inadequate. On the other side, American engineers at Packard, perhaps without fully understanding how their work affected adversaries on a psychological level. American pilots flying Mustangs, confident in their machines but perhaps unaware of how much their superiority was a product of vast and invisible industrial systems. Modern conflicts create these ironies and disconnections. Decisions made in design rooms in Michigan directly affect the experiences of pilots over the Pacific. Metallurgical capabilities of steel mills in Pittsburgh determine the outcomes of aerial encounters over the Philippines. Educational systems that train engineers at American universities decades before the conflict contribute to developments in 1944. Everything is connected. Everything is part of larger systems that no individual fully controls, but to which everyone contributes in some way. The photograph of those engineers surrounding the disassembled engine deserves final contemplation. It's an image frozen in time, capturing a moment of profound human discovery. Those men are looking at something that will completely change their understanding of the world. We don't know exactly what they were thinking at that precise moment, but we can imagine. Perhaps admiration for engineering. Perhaps concern about what discovery means. Perhaps professional respect crossing lines of conflict. Perhaps simply intense concentration on the technical task at hand. Probably some combination of all of these. What we know is that that moment, multiplied by countless similar moments over weeks of meticulous study, transformed these engineers' understanding of war, of industrialization, of the future of their country. And this transformation, although initially restricted to a small group of technical specialists, eventually contributed to the broader transformation of Japan in the following decades. History sometimes works like this. Small moments of individual discovery accumulate, spread through societies, and influence developments that ultimately change the world. The Merlin engine itself was the product of a century of aviation development. From the Wright brothers' first flights to refinements accumulated by dozens of aeronautical engineers working in multiple nations. Every small improvement, every incremental innovation, every problem solved contributed to that engine which Japanese engineers examined with such attention. Technology advances in this way, through the accumulated efforts of many, building upon knowledge inherited from previous generations, constantly refining, gradually improving, until something extraordinary emerges from the sum of countless individual contributions. And now we come to the end of this long story, though its reverberations continue to this day. The engineers who studied that engine are gone, their lives concluded. The P-51 they captured was probably destroyed in the final chaos of the war or dismantled so completely that it ceased to exist as a recognizable aircraft. The Merlin engine continues to exist in preserved examples in museums, still occasionally heard roaring through the sky when enthusiasts fly restored Mustangs at air shows. But the moment of discovery, that moment when Japanese engineers truly understood what they were facing, now exists only in faded memories, in archived reports, in stories told by those who were there to those who came after. However, the lessons remain. About the importance of seeing clearly. About the role of industrial capacity in modern conflicts. About how technology incorporates not only technical knowledge but entire systems of social organization and economic production. About the courage to confront difficult truths. About how individual moments of discovery can influence the course of nations. About the shared humanity of engineers on opposing sides, united by professional respect even when divided by war. The story of the Merlin engine and the Japanese engineers is, in the end, a human story. It's about extraordinary people in extraordinary circumstances, trying to understand their world, applying their skills as best they could, confronting realities they would rather not face. It's a story that deserves to be remembered, not just as a technical curiosity or a military footnote, but as a testament to the human experience in all its complexity. Brilliant and tragic, revealing and painful, specific in its details but universal in its implications. May the Lord God enlighten those who seek knowledge with the courage to see the truth clearly, the wisdom to apply that knowledge wisely, and the compassion to remember that, behind every technology and every conflict, there are always human beings trying to find their way in a complex and often difficult world.